So here I want to use the same technique I just used to solve the Fibonacci sequence recurrence relation to do this more generalized case here where I have these coefficients a, b, and c, which could be any real numbers. So this is called the second order linear constant coefficient homogeneous recurrence relation. The reason it's called homogeneous is because over here you could have a different known function of g over there, but instead I just have 0, and that makes it easier to solve. So I would recommend watching the last video first because I want to kind of go quickly through this first part. So first thing I want to do is define a generating function here. I'm just going to take each of the terms of the sequence and attach those to an x to the n. Then if I have this power series here and I multiply by x, effectively what that's going to do is it's just going to shift the f0 is now going to not be, it's not going to be the constant term, but it's going to be the linear term, and these all just shift over 1. And if I multiply it by x again, then it shifts over like this. And the idea is from here, you can see that we have these like terms here, the f2, the f1, and the f0. If I can add these together in such a way that I can apply this recurrence relation here, then I should get some stuff canceling out. So if I take a times the first row plus b times the second row plus c times the third row, then I'll have af2 plus bf1 plus cf0, and that would give me 0. And so with this, and all the next rows would also be 0, or the next columns. So here I've done that. You'll notice that you just end up with this over here. You end up, these cancel, or these don't cancel out over here, this triangle. And the f0 and the f1, those are called your initial values. And so, for example, with the Fibonacci sequence, you have that f0 is 0, f1 is 1. Those are your initial values, and from there you can get a unique solution. So in this case, I'm just looking at general solutions, so I'm just going to leave those in there. You can solve for f of x by dividing by this factor over here, and then you get this. You see that f of x is just a rational function. Since this was a second order equation, you ended up with a second degree denominator here, and the numerator is 1 degree less than the denominator. You can see that that would always be the case, and this actually generalizes really easily for higher orders. If you had a third order, you'd just have another equation here, and your triangle would become this thing here, containing your initial values f0, f1, f2. One comment I want to make here is that I just added infinitely many terms together a bunch of times, and so that's only a valid technique to have all this stuff canceling out like this. This is only valid for convergent sums. And so the question is then, like, is this sum here convergent? And the answer is that it depends, and it depends on x. So x, like this series isn't really concerned about x. X is constant as far as it's concerned. So like this thing here, you might think of this as like a power function, but it's a power function of x. It's really an exponential function of n. So you can just imagine if x was 1/2, then what you'd have here, this would be a decaying exponential function. And if x was 2, then you'd have an increasing exponential function. So the question becomes, what is f of n? That's going to tell you whether or not this thing converges or diverges, and the problem is that you don't know f of n. That's the solution to this problem. So you can imagine if it were a constant, then this would just be a geometric series, and it would have a radius of convergence of x would have to be less than 1 in magnitude. And you can imagine if f of n, for example, if it were 1 over n factorial, then what you'd have is the Taylor series for e to the x, which is convergent for all real x, and that's because the factorial, you pretty much have like a battle between factorial function and an exponential function, and the factorial function wins. Since it's in the denominator, it forces this thing to converge. So my claim is that the solution to this type of recurrence relation allows this thing to have some radius of convergence around 0. You might be able to whip up some kind of epsilon delta kind of proof to show that this thing is continuous around 0, but it's pretty easy to show that 0 itself is a convergent value for this series. If you look at what is f of 0, if you look at this one here, you can see these all just cancel out and it's just big F0. Similarly, if you look at this expression here, if you plug in 0 for x, these cancel, here you have a over a, those cancel out, and you just get F0, which is consistent. So my claim to you is that there is some radius surrounding 0 where this is convergent. So I'm going to say that this is valid for when x is less than some radius magnitude, some real number there. And if you don't believe me, that's fine, because you can still get to the answer and then you can prove that it was right using induction. I might make a video for that, I might not, I'm not sure yet. So the idea from here is we want to take this thing, do a partial fraction decomposition, and get it into so like if we do a partial fraction decomposition, this is going to have, it's going to become two rational functions, each with a linear denominator, and we can use, or we can make those look like a geometric series. So, so I'm just going to do that right here. So f of x, this is going to be a over x minus x1, the first root of the denominator, b over x minus x2. And so I'm making another assumption here. This is really only, this form only works if you don't have a repeated root. If you have a repeated root, then you'd have x minus x1, and you'd have another x minus x1, but it would be squared. So you have to do this on a case-by-case basis, and in this video I'm just going to focus on the case where you have no repeated roots in the denominator of the generating function of f of n. So I'm just going to write that over to the side here. No repeated roots allowed. So what I can do from here is I can just pretty this up a little bit so that I can get it into a form where it looks like I can relate it to a geometric series. So all I'm going to do is make a couple aesthetic changes here. I'm going to take this one here, I'm going to divide top and bottom by -1 over x2. And then I'm going to take this one and I'm going to divide top and bottom by -1 over x1. And so I'm actually making another assumption. You can't divide by 0, so I'm also assuming that x1 and x2 are not 0. And so we could do that in a separate case, but it's pretty easy to see if you have a root of 0 in your denominator, that would mean that this a here is 0. And if a is 0, if you look back at this original recurrence relation here, that would mean that this term is 0. And so you just have a first order equation, and you wouldn't be going through all this work in the first place. When you generalize this up to higher orders, that would just mean your leading coefficient is 0. So as long as you assume that your leading coefficient is non-zero, then you won't have a problem with these 0 roots here. So what I can do here is I can just define some new constants here. I'm not going to talk about a and b anymore. I'm going to say a times -1 over x1. I'm just going to call that c1. And this one I'm just going to call c2. And in the denominators here, what I'm going to get, the reason I divided by -1 over x1 in this case was because that'll turn this minus x1 into just a 1. And here that'll turn this minus x2 into a 1. And then what I'm left with over here is I have negative x over x1. And so instead of writing x over x1, I'm just going to write lambda 1x. And over here I'll write lambda 2x. So I've just made a couple new constants here. No big deal. So now these are in the form of geometric series. And so what I can do is I can replace that with the with the series thing, and then I should be getting closer to some way to see what this f of n thing is anyway. So f of x here, this first one is just going to be c1 times the sum from 0 to infinity. This is just, the argument here is just going to be lambda 1x, it's to the n. And so the next one, it's just the exact same thing, it's just with a c2. And this is just lambda 2 x to the n. And so then when is this valid? Well, this is valid if lambda 1 times x, that's my argument here, the absolute value of this is less than 1, and in this case lambda 2x is less than 1. If you're wondering about that, watch my video on geometric series. And so I can rearrange these to find out what that tells me about x. This one tells me that x must be less than 1 over lambda 1, and here x must be less than 1 over lambda 2. And so what I can do is I can take this f of x thing here and I can just combine these. These are just two series. I'm assuming they're convergent. I'm only using the convergent part of them. And so what I get, I can bring these constants inside first of all. I'll have this c1, and I'm going to put this lambda 1 to the n here along with it. I'm going to factor out the x to the n in both cases because those are common term. Over here I get c2 lambda 2 to the n, and then this is all times x to the n. And so what you find out, this coefficient here, this is dependent only on n, is the same as this, since this is also f of x. So you get f of n is equal to c1 lambda 1 to the n plus c2 lambda 2 to the n. And when is this one valid? Well, this is only valid if both of these were valid. So in other words, this statement has to be true and this statement has to be true. And so what that means is I can just stick with the one that's more specific. So it's kind of nice, since I have all these absolute values here, it makes it easier to think about. X just has to be less than the lesser of these two. So this is valid if x is less than the minimum of 1 over lambda 1 and 1 over lambda 2. And if you think of what this means, if you go back to over here, lambda 1, that was just 1 over x1. Lambda 2, that was just 1 over x2. So in other words, we're saying that x needs to be less in magnitude than the magnitude of either of the, or both of the roots of the denominator. So if you think of what that looks like graphically, which doesn't really matter, now we've got our solution here already, but anyway, if you think of what, if you think of the graph of f of x, what does this look like? I could draw a picture, and let's say I know where x1 and x2 are. I'll just put x1 here, and I'll put x2 here. So since x2 is closer to the origin, my interval of convergence is just going to be from here to, it's symmetrical, so it's just going to be from here to negative x2. In this case I picked x2 as a negative number, so this in here is my interval of convergence, and we know that f of x, since one of the roots of the denominator is x2, that means that it has an asymptote right here. Asymptote. So this, if you think of what this looks like, it's going to come down like this, and then it's just going to abruptly stop here. And so this is really what f of x looks like. Of course, you could look at the continuation of it too. You really have this rational function going over here, and this part really, it's going to continue here. You're going to have another asymptote here, something over here. And one other thing I want to mention, this video is going really long, but which is why I'm trying to talk fast. Lambda 1, x1 and x2 could also be complex numbers. If you're used to doing partial fraction decompositions for the purpose of integration, you might be used to only separating them if you don't have a irreducible quadratic. But really, even if you have an irreducible quadratic, you can reduce these, and you're just going to have complex roots. And if x1 and x2 are complex, that means lambda 1, lambda 2 are complex. And so all this stuff still holds, this geometric series stuff. These absolute value signs, those just represent the magnitude or like a complex argument on the complex plane, distance from the origin in the complex plane. So you could even draw a picture of the complex plane here to look at the very least, at the domain of f of x. And what this would be you're going to have like your smaller of the roots here. If you look at the magnitude of it, I could just say this point right here, this would be absolute value of, let's say, lambda 1, if that's a smaller one. Then what you're going to have is this region of convergence here that's going to be this disk without the border on it. Whoa. Okay,